is project 1, video number 3, the one in which we do the documentation and finishing touches. So let's see, we do a comment here, the problem being this function. So you actually have to explain what's going on here. Say what the function is for, and what it does, and then you gotta say by, and then input variables. Q percent RVEC you got to say what it is. Explain what it is. If you decide to go this way with the RVEC instead of like calling it something like coordinates or something, make sure you explain why you call it RVEC. That you know, the idea that for the case of the position vector, a position vector of a point in space relative to the origin, it's going to have components that are exactly the same as the coordinates of the point in space itself. So you want to explain that, and then we got percent output, I just say variable, and then what do we have? E vector. So explain what it is. Make sure you say it's a 1x2 array as part of your explanation. Oops. 1 times 2 array. And you got a lot more to write there. And then I think the notation I've used makes this self-documenting. This is the Coulomb constant. Somebody working with charged particles, I'm going to assume they know that's the Coulomb constant, so I'm not even going to say this is the Coulomb constant. That's the standard name for it. And, it's pretty obvious, especially when it comes down over here, down to the KQ over R squared. That works out. The R hat times Q, where if Q is negative, this E vector still has the correct direction. I don't think we need to explain that either, so I think we need say what resources you used to write the code. And tell me a little bit of a story here, if you would please, like explaining how you did it on your own, for instance, if you did it on your own and you never had to look anything up, or in which case I would expect this RMAG, I'm not sure everybody knows, I just happen to know, or in the back of my mind I was pretty sure there was something called norm that would work. But you certainly didn't have to use that. You could have used RMAG is equal to the square root of RVEC 1 squared plus RVEC 2 squared. So you didn't have to use that. The other thing, you could have done this completely differently with you know, where I'd find some angle being measured, and your x component of the electric field in the end is going to be your total electric field times the cosine of that angle. And the y component of the electric field is going to be the total electric field times the sine of that angle. So you didn't even have to use this unit vector, the ijk, which turns out to be just ij in the case of a problem in a plane. Ij unit vector notation or ideas. And in some sense, I don't have the notation there because you never see an I hat or a j hat, but that's the idea that I used. You could have used one where you find the total vector and then break it up into its components, and then stick the components into a 1x2 array in the end. But okay, I actually think I'm done, but let's go through the checklist. So I guess first off, let me make sure it does what they said to do. Write a function that calculate the electric field. Yeah, it takes two arguments, and the order they're specified here. So a scalar value first, representing the charge. There we go. Considered to be fixed in space. The charged particle is fixed in space by means not specified at the origin. Then a 1x2 array, and that's R back. First element contains x, with the coordinates. And then it returns a 1x2 array, my E vector, which down here we see turns out to be a 1x2 array because R hat by this time is a 1x2 array because R vec is a 1x2 array. The x component of the electric field, the y component of the electric field. Okay, so I think we're good. Then checklist, complete algebraic solution. I don't know how complete folks consider this, but especially with the example that I gave, I guess it is pretty complete. With at least one diagram. Here's the diagram. You would have more diagrams probably if you decided to go with, defining an angle, finding the magnitude of the electric field, and then breaking that up into its components. You need a vector component diagram as well as other stuff, but I think we got it. This, I should have put at some point the electric field on there. Let's fix that up at this stage. So the electric field at this point, that'll be the electric field for the case of a positively charged particle. Be in the exact opposite direction if it's actually negative. Okay, so complete algebraic solution. How do you find E? So I got E vector itself as the bottom line. And then what else do I need? I'm sure code out for each function outline of the steps the program will execute. The pencil and paper part. Oh, here's the outline, code outline. Initialize, take these two arguments. I probably should reverse the order, but I think it's okay. Calculate R mags. I didn't actually use this formula, but I used that norm function. Calculate R hat. I think, while I'm thinking of it, let's run it once with the negatively charged particle and make sure that I get negative value, so it would be directly toward it. Also, if I was in the lower right quadrant, minus 0.1 for instance, insert a minus sign right there and run it. So if I'm in the lower right hand quadrant of a coordinate system, let's see, if the point was down here and it was a negatively charged particle, I would expect that the electric field would be up in this direction, which would be a minus x component and a positive y component. Let's see if is that what I got? Yeah, minus x component, positive y component. Oh, and I was way down. Look at that, minus 1 meter. So it would be almost straight up. So I was like way down here. So yep, that does make sense. Alright, what else? I think I should keep on trying to check it. Let's see what happens if point P is at the origin. Well, first off, if it's on the x-axis, I expect it to point straight along the x-axis. We'll just do a couple of test cases here. I think I'm interrupting this up, but I wanted to do some tests while I was thinking of it. I haven't finished doing some of the other stuff I got to do. So, if it's on the x-axis, then I'll go with a positively charged particle. Then it should be pointing in the plus x direction, so we should have some number comma 0. That's cool. If it's a 0, 0, I would expect it to blow up. So r is going to be equal to 0. So in some sense it shouldn't work here. Let's see what kind of error we get. Yeah, we get not a number, not a number, which is telling us that it divided by 0 and got its infinity, and they just put NaN for that. So it's failing where it should fail. Alright, let's get back to checking this stuff. That was the pencil and paper part. And I was talking about the next thing I got to have is code outline, and it looks like I got a code outline all the way to calculate and return evec, so that's good, and that's just the way I programmed it out too. One point for a reasonable attempt at writing the program, you got to have one or more .m files, so it is this thing that's got to be submitted. I'm going to do Control S to save it, make sure I've saved it. Guess I'm not sure I've run it after I saved it, so we'll run it with that X case again. Yep, still seems to be working, and indeed if I put a semicolon after it, nothing's printed out. Okay, still working. If I make any more changes, hopefully I'll remember to check it again. Reasonable attempt, one that works properly. Based on my checks, it does work properly. Results in nothing being printed to the command window. If you include the semicolon, that's cool. You must have your name in it. Oh, there it is. Thought I'd forgot that for a minute there. Your code must be documented. Comment. Well, I didn't actually do it. You have to write the comment there. I have a little writing exercise for you, stating what the function does. And another set of comments. So up here you got to say something like it solves for the x and y components of the electric field at some empty point in space due to a charged particle having charge q at the origin, or a particle having charge q, where this is the q. And where is it? It's at the position whose coordinates are stored in rvec, or you could say its position is determined by the position vector whose components are stored in rvec, same thing for this particular case. List of arguments of the function, the input variables. For the case of a function that returns one or more values, it does that. List of the return variables. Well, we've only got one, but you got to make sure. I think I've kind of messed that up there. Delete. Move that up there. Maybe space it over a little bit. There we go. Easier to read that way. And then maybe I'll put one more line in there before the code actually begins. Alright. get that. For the case of function that includes segments, I found them all self-explanatory based on the notation that I use, like the standard K for the Coulomb constant. You must provide attribution. Make sure you write it in your own words. Again, tell me a story, like how you arrived at this. If you just did it all on your own and then you checked mine and yours was right, say so, and say you consulted the videos made by Professor Schnick for Project 1, but didn't have to make any changes there. It was just to check to make sure everything was okay, etc. So whatever the actual story is, please tell it. And that does it for Project 1 Video 3.